All right, y'all, this is going to be note card number 6, continuity. And before we actually start with the note card itself, I want you to go ahead and draw these 3 graphs. Okay. Now first, I'm just going to tell you which one of these 3 graphs are continuous and which one or which ones are not. Okay. So in this first example, this graph is continuous. This graph is not continuous, and this graph is also not continuous. Now, all 3 graphs kind of look the same. There's some common features to it. First off, it looks like some sort of polynomial function, maybe like a cubic or an x cubed function going on here. Okay, so I want to kind of go over what continuity is and what continuity is not. There's basically 3 conditions that have to be met for a function to be continuous. So let's just call, in each case, let's just call these functions f in each case. So for a function to be continuous, okay, these 3 conditions have to be met. First condition is that f of c exists. Okay. The second condition is that the limit as x approaches c from the left of f of x has to be the same as the limit as x approaches c from the right of the function. So that's the second condition. And basically, if number 2 is true, that implies that there is a limit. If each of the one-sided limits are the same, then that means that. So that's just another way to write that. And the third thing is the limit as x approaches c of f of x, it's got to be the same thing as f of c. Okay. So for any condition, or for any function to be continuous, it has to meet all 3 parts. It's got to meet all 3 conditions for a function to be continuous. Okay, and here's the easy way to think about continuity. When I draw this graph, I can draw this graph. Remember, a point, a filled-in point, is just part of the actual function itself. So the way I like to think about continuity is with a pencil test. Can I draw this function without picking up the pencil? Yes, I can. That's continuous. Now on the next function, okay, this open circle represents a hole in the graph. So what this really means is that I come here and then I have to, there's a little hole, so I have to pick up my pencil to go to the other part. So it doesn't meet the pencil test there. And same thing here. I have to come up here, I have to pick up my pencil to draw the rest of it, and I have to pick up my pencil again to fill in that point. That's not the same as the open circle. Okay, so let's kind of go over each of these 3 graphs, and let me tell you why it meets all 3 conditions. Okay, so in this first graph, all right, here's a filled-in point. Okay, there's a filled-in point. So here, f of c, okay, when I input c as the x value, it comes out with a y value of L. All right. So in this case, the function value, the y value or f of c exists because that's a filled-in point. Okay. Now here, in the next graph, f of c, when you plug in c, this is an open circle, so it doesn't have a y value there. So here, f of c does not exist. Right away, this is not, it doesn't meet the first condition. Okay. Now here, on the third graph, when you plug in c, you take it up to find where the filled-in circle is, and there it's m. Okay. So graph 1 and graph 3 both meet the first condition. So far so good on these 2. This one, it's not continuous because it doesn't meet It doesn't meet the first condition. All right, now, what about this next one? Okay, what about condition 2? Well, as I get closer and closer and closer to an x value of c, here, so I'm getting close to c, I'm getting closer to a y value of L. So on this one, the limit of f of x as x approaches c from the left, so I come in from this side, I'm getting closer to a y value of L. Okay. And what about as I come in from the right side? Well, as I come in from the right side, I'm also getting closer to a y value of L. So that's going to be the same thing as the limit of f of x as x approaches c from the right. So the left limit does equal the right limit. So that meets condition 2 for the first graph. And what about the next graph? Okay, as I come closer to c, I'm approaching a y value of L. And as I come in from the right side, I'm also approaching a value of L. So this one's good. All right, this graph is good for the second condition. The limit as I approach from the left equals the same thing as the limit as I approach from the right. So here, even though that this is an open circle, the limit still works. Okay, the limit there is still L. And also in this last graph, as I get closer and closer and closer to C, but before I hit C, I'm also approaching a value of L. That equals the same thing as when I approach from the right. Okay, and in both cases, I'm approaching L. Okay, I'm not approaching M. The graph itself, I'm approaching a y value of L. So if we kind of make little check marks here, so graph 1, graph 2, graph 3. Okay, so in graph 1 and graph 3, the function value existed, but it didn't exist there. Okay. And condition 2, in each case, it worked. Okay. The limit was L in each graph. Now, what about the third condition? This says that the number that you approach, the y value that you approach, that's what this is saying, equals the same thing as the function value. Okay. Well, here, let's kind of check it out. All right, in graph 1, I'm approaching L from both sides, and the function value also equals L. So that one works. Okay. But in graph 2, even though I'm approaching L, there's no function value there. The function does not exist there. Okay, so here, this thing equals does not exist. So it can't be true. So it fails that condition as well. It fails condition 3. Okay. And in the third graph here, the limit existed, so the limit was L from both sides, but the function value itself is M. These two things do not equal each other. L does not equal M, so it fails the third condition. So only graph 1 meets all 3 conditions. Okay. The second graph failed the first condition and it failed the third condition. And the third graph met the first 2 conditions, but it failed the third condition. Now you must know these 3 conditions, because on the AP exam, they might ask you about continuity. And whenever they ask you about continuity, you have to state these things and whether they're true or not. It has to meet all 3 conditions for a function to be continuous. But the way we think about it is, does it pass the pencil test? Could I draw the graph without picking up my pencil? That one you can, these 2 you cannot. So that one's continuous, those are not continuous. And when we talk about continuity, we talk about continuity at a single point, or at a given point. And in each of these 3 cases, I'm talking about the continuity at point C. Okay. Now, the rest of this graph, or excuse me, for graphs 2 and 3, the function is continuous at everywhere except for C. But at C, it's not continuous there. And at C, it's not continuous here. So like here, at this point, it is continuous. At this point, it's continuous. At this point, it's continuous, so on and so forth. But as a whole, the function's not continuous because it's not continuous everywhere. That's not continuous there. So if something's not continuous, just some terminology, then that means it has a discontinuity. Or it's discontinuous at a certain value. And in both of these cases, it's discontinuous at an x value of c. So that's basically continuity. Okay. Does it meet the pencil test? Formally, it doesn't meet all three of these conditions. Now let's jump into the note card itself. All right. And on note card 6, there's the same things that I just wrote, the three conditions, but there's also some other properties of continuity. So what does this mean? So like if you take a function f that's continuous and you just multiply it by a constant, then that would also be continuous. If you have two functions f and g, and if both of those are continuous, then when you add or subtract those functions, the sum or the difference would also be continuous. Same thing with a product. If f is continuous and the function g is continuous, if you multiply them, they're going to be continuous everywhere. All right. Now, what about quotient? If f is continuous everywhere and g is continuous everywhere, if you divide them, they'll also be continuous as long as the g function never equals 0. If the g function equals 0, you know you're not allowed to divide by 0. And likewise, if you take a composition of functions, if both f and g are functions and they're both continuous, if you compose them with each other, that'll also be continuous, as long as it doesn't come out to be some rational function. Okay. Now, thinking about some functions itself that are always continuous. Okay. So if you have like a polynomial, like a x plus 4, or an x squared minus 5, or an x cubed plus some other stuff after that, those are always continuous. There's never any gaps in it. Now, rational functions are continuous as long as the denominator can never equal 0. If the denominator equals 0 at a certain point, then it's not going to be continuous at that point. Power functions are continuous. Exponential functions are continuous. Logarithms are continuous over its domain. So like logarithms, like a ln, a natural log, or a regular log looks like that. As soon as the function starts, it's continuous, but it's not continuous usually over on this side. And some trig functions are continuous everywhere, like sine functions and cosine functions are continuous everywhere. But once you start getting into some of the other ones, like tangent's not continuous everywhere, and the reciprocal functions have some asymptotes. Okay. Now, if a function is discontinuous, there's some different types of discontinuities. So let's talk about some of those. Okay. So, okay. If you have a graph like this, if you have something like that, okay, with a open circle, this is what's called a removable discontinuity. That's called a removable discontinuity because if you exclude that value, okay, if you exclude that value, or if you remove that value from the domain, it's continuous everywhere else. So that's called a removable discontinuity. All right. Let's look at another type of graph. Here, this is called a jump discontinuity. Okay, it's called a jump discontinuity. All right, because the function looks like it's either jumping up or jumping down. All right, and the last type of major discontinuity you can get is if you have some sort of asymptote. If you have a function that kind of looks like that, there's a discontinuity here at this value. Okay, so that's an asymptote. That's a vertical asymptote. And in a graph, if you have any one of these three types of discontinuities, it's not continuous at that value. Okay, or you could have a graph with several holes. They're not continuous at these values where these three things happen. Okay, so those are the types of, the most common types of discontinuities. Okay. So let's go ahead and look at some of the problems given on this note card. Okay. So number one, it says, for what values of x is h not continuous? And justify. What type of discontinuity exists there? Okay. So in the first example, h of x, it's a piecewise function. There's three pieces. Okay. The first type, if you just recognize this function, it's a linear function. The second part here, that's like y equals 3. That's just a horizontal line. Okay. That's just a horizontal line, but it's only good at a certain point. Okay. And the last part here is some sort of cubic function. Okay. So there's different ways to approach this problem, but for now, let's just go ahead and graph it. Okay, let's go ahead and graph it. Okay, so the first piece said, or they're calling it h of x, no big deal. Okay, so the first part said, the function represents a line, negative 2x plus 3, when the x values are less than negative 2. Okay. So at negative 2, let's think about that. Here's an x value of negative 2. Okay. This line only applies for values that are less than negative 2. Okay. So what about if there was a little bar underneath here? Well, if there was a bar, that means it would be included. So this one's not going to have an included point. But let's think about what it would be. So if I plug in negative 2 here, negative 2 times another negative 2 is positive 4, plus 3 would be 7. 1, 2, 3, 4, 5, 6, 7. Now I'm going to put an open circle at 7. Oops, that's not 7, that's 6. Here's 7. So imagine that's not a fill-in point, sorry. And what about if you plugged in negative 3? Negative 2 times negative 3 would be positive 6, plus 3 would be 9. 8, 9. So when x is negative 3, the y value there would be 9. Okay. So there's that graph. And you could keep plugging in more and more points. Now, how do I know it's going to look like this? Because this part of the line looks like it has a slope of negative 2. So it means I go down 2, I go over 1. So that's negative 2 over 1. Okay, and again, there's an open circle here because there's no bar underneath the 2, the negative 2, excuse me. All right, now what about the next part? It says, that's like saying the y value equals 3 when the x value equals exactly negative 2. So that's actually a single point. So when x equals negative 2, the y value equals 3. So negative 2, and you go 1, 2, 3, up 3. And the last one is a cubic function, x cubed minus 6x plus 3. And that's only good when the x values are greater than -2. So what would happen if I actually plug in -2 here? I would have -2 cubed minus 6 times -2 plus 3. -2 cubed is -8. -6 times -2 is +12. Plus 3 at the end here. 12 plus 3 is 15. Minus 8 would be 7. Okay. Now you can plug in other values. What would happen if I plug in 0? Okay, because 0 is a number that's bigger than -2. 0 cubed minus 6 times 0 plus 3. Hopefully you'll just say that's 3. Okay. So we would get another open circle at +7. Okay. And we said when the x value is 0, we would get a y value of 3. What about when the x value is -1? -1 cubed minus 6 times -1 plus 3. That'll be -1 plus 6 plus 3. Okay. And that would be 8. So when x is -1, the y value would be 8. So this graph kind of looks like this. And then probably at some point, since it's a cubic, it's gonna turn again. Okay. So looking at that graph, let's identify what type of discontinuity it is. Okay. If I could change this y equals 3, if I could change that to a value of 7, then we could move this point and fill in that hole. Okay, so this is actually a removable discontinuity. Because if we could remove or change this point to move it up, if I could take this 3 and turn it into a 7, then I would pass the pencil test. Now I can't pass the pencil test here because I have a filled in circle. Okay, and if you look at that graph, there's only one value where it's discontinuous. So this function is discontinuous at an x value. Where's the hole? Well, the hole happens at -2. So everywhere else it's okay, but it's discontinuous at x equals -2 because there's a removable discontinuity there. Okay. So did you have to graph it? No, you really didn't. There's an easier way. Okay. What I could actually do is I could plug in these numbers. Okay. So all I would have to do is plug in -2 times -2 plus 3, and we found that to be 7. What does that mean? That means the limit as x approaches -2 coming in from the left of h of x equals 7. So by plugging in -2 here, I'm finding the left limit. Okay. Well, what is the function value itself? What's h of -2? Well, when the x value is -2, the y value is 3. Okay. And what about the right limit? Well, the limit as x approaches -2 from the right, I'd be using this green part. So when I plugged in -2 here, I got 7. So if you think about the definition of continuity, here the left limit equals the right limit. When I plug -2 in there, I get 7 as well. Okay, so the left limit equals the right limit. So that met condition 2. The function value exists, so that met condition 1, but where does it fail? Which condition does it not meet? It doesn't meet this third condition. The limit doesn't equal the function value because 7 does not equal 3. Or on the graph, you can see that. Here, this is the limit 7, but the function value is 3. So there's the connection between the graph, that piecewise graph, and then just evaluating it by plugging in values. Okay, it's the same thing. I didn't have to graph. Sometimes graphing gives you a bigger picture of what's going on, but you didn't really have to graph it. And obviously this would be some sort of removable discontinuity, because here it's less than and greater than. So you have open circles. You're dealing with open circles. And that open circle does not get filled in because this y value is 3, not 7. That's why it's removable. Now let's think about number 2. It says, if the function f is continuous and f of x equals this function as long as x doesn't equal -2, then what would f of -2 equal? Well, let's think about this real quick. So if I do some simplification of f of x, I see here that this is the difference of 2 squares. All right. So that's going to factor into x plus 2 times x minus 2, and it's going to be over an x plus 2. That's this part. Okay. And what you'll notice there is that those cancel each other. So what does the graph of f of x look like? It looks like a simple linear function, 1x minus 2, as long as the x value doesn't equal -2. Now, how do I know that? Because -2 would make this thing equal to 0. And you know you're not allowed to divide by 0. So what does this graph actually look like? Let me show you. I'll show you what this graph looks like. So here's the graph. F of x equals x squared minus 4 over x plus 2. And we said it's going to be exactly the same thing as the graph of x minus 2 as long as x does not equal -2. So what does this graph look like? 1x minus 2. That means it has a y-intercept of -2 from that, and its slope is 1, or 1 over 1. So rise 1, run 1. Rise 1, run 1. So the graph kind of looks like that. That's what that rational function looks, or that's what this looks like. But there's one catch. Because you have a denominator here, if you gave me an x value of -2, -2 plus 2 would equal 0. So when x equals -2, what that creates on the graph, it creates a hole. That's why we get the removable discontinuity there. Okay. Now, let's go back to the problem. Now they're saying, well, let's pretend that we could fill that in. Okay, let's pretend that we could actually fill this hole in. All right. And let's say we could take away that removable discontinuity. What would the function value equal there? What would the y value equal there? Well, all I have to do to find that is I just have to plug in this -2 to the simplified expression. So when I plug in -2, 1 times -2 minus 2, that's -2 minus 2, that's -4. So if we could fill that in, the function value would be -4. That's the y value. F of -2 would equal -4. But in reality, in the graph, it's really an open circle. So the function value really doesn't exist. They're just saying, what about if we could fill it? That's what the question's asking about. Okay. Number 3, it says, which of the following functions are continuous for all real numbers x? This is where your knowledge of graphs will help you. Okay, so let's look at number 1, x to the 2/3 power. So if you think about this, this is like saying the cube root of x squared. Okay. Now think about what type of values you're allowed to stick in for x. Well, if you took negative numbers and squared them, you would get positive numbers. Okay, this part inside the radical would be positive, and cube roots of positive numbers are always positive. What this graph actually looks like, it kind of looks like a seagull graph. Okay, you're allowed to have any x value you want. That graph's going to look like a seagull graph. Okay, so if I think about this, I don't have any gaps, and I could draw this without picking up my pencil. Okay, the next graph, an exponential, natural exponential graph. That graph looks like this. Okay. I can draw this graph without picking up my pencil. So 1's continuous everywhere for all real numbers. 2's continuous for all real numbers. Even if you plug in negative numbers here, it's still okay. Okay. But the third graph, a tangent graph, if you remember tangent is the same thing as saying the sine of x over the cosine of x. Well, this might create a problem whenever the cosine of x would equal 0. So where is the cosine of x going to equal 0? Well, it's going to happen at 90 degrees. It would happen at negative 90 degrees. It would happen 180 degrees, every 180 degrees after that. So it would also happen at 270. So this graph has asymptotes. This graph has vertical asymptotes. Here's what the graph would look like, okay, on both sides. And vertical asymptote is a type of discontinuity. So this is not continuous everywhere, okay? There's problems when we get to 90 degrees, 270, 450, so on and so forth, every 180 degrees after that. So 3 is not continuous everywhere. This is one of the trig graphs that is not continuous everywhere. The only two trig graphs that are continuous everywhere are sine and cosine. Okay, so only 1 and 2 are continuous everywhere. So that's the right number. Okay. Now, number 4, okay, it says, for what values of the constant c is the function g continuous over all the real numbers? Okay, now we don't know what c is. That's our goal. We're trying to figure it out. But what we want to happen here, for the graph to be continuous, all right, if you think about this, when you plug in a number for c, this is just some sort of a line, and this is just some sort of parabola. And here's where the function changes. It changes at an x value of 3. So I don't know what the right number for c is right now, but at 3, what's going to happen for this first part, okay, let's say c was a positive number, so that means it would be a positive slope. So it would be coming in kind of like this, and it's going to be a filled-in circle there because that part has the bar. Now, the way I can make this continuous is as long as the parabola meets here, meets at that point, that part's going to be an open circle because there's no bar under here. Okay, so if let's just say it kind of looked like this. But since this is a filled-in point from the first piece, then it overrides the open circle from the second piece, so I can draw that without picking up my pencil because the filled-in circle overlaps with the open circle. So basically, as long as the left and the right limits equal the same thing, then we're going to be okay. So here's what we're going to do. Let's evaluate the left limit, the limit as x approaches 3 from the left of g of x. How are we going to do that? All we're going to do is plug 3 in for x in this first function. So when I plug 3 in, this would be c times 3 plus 1. Or a nicer way to write that would just be 3c plus 1. Whatever c is, that's, okay, this is a x value of 3. Okay, I'm just going to plug that into the first function. Now, how do we figure out what the right limit is? We're going to approach 3 from the right side. So how are we going to figure that out? Well, we're going to plug 3 in for the x there. So we're going to do c times 3 squared minus 1. If I do some simplifying, 3 squared is 9, c times 9 is 9c minus 1. Now, how do we make sure that these come out to be the same y value? Well, all we have to do is we just have to set this 3c plus 1 equal to the 9c minus 1, and we solve. Okay, so this just becomes an algebra problem. 3c plus 1 equals 9c minus 1. Subtract 3c from both sides. Okay. Hello? Yes. Okay. Sounds good. Okay, thank you. Bye. All right, apologies about that. All right, so we subtracted 3c from both sides. Just add 1 to both sides. Okay, that'll make those go away. Then you'll have 6c equals 2. Divide both sides by 6. And c would equal 2 over 6, which I can simplify to 1 over 3. So as long as c equals 1/3, then the function is going to be continuous. The function will be continuous there. And what this y value will actually be, it'll come out to 2, because if I plug in a third here, 3 times a third is 1, plus 1 would be 2. And if I plug in a third here, 9 times a third would be 3, minus 1 would be 2. So when I plug in that number, the left limit would equal 2 and the right limit would equal 2. And then the function value would also equal 2 because that's the filled in circle. So it meets all the parts of continuity. Okay, so that's basically this note card. Okay, so you'll get more practice here in packet 6. There's some review questions. There's some more limit questions just looking at this graph. Okay, you get more experience with graphs and some other piecewise functions. Usually your questions about continuity come from piecewise functions on the AP test to make sure you understand what continuity is. Okay, so just work on those this evening or when you get a chance, and then go ahead and just note your questions and we can go over those. Thanks for watching.